Okay, here we will introduce the current carrying coil as a magnetic dipole. So actually, of course, in this figure, you can see there's a magnetic bar and also a current carrying wire. But actually, it means that they don't need to occur at the same time. Okay, if we have a magnetic bar, it will generate the B field lines, like the green lines. Okay, or if there's no magnetic bar and we only have this current carrying coil, it can also generate the B field lines, actually like this. So we will say that this magnetic bar and the current carrying coil is equivalent to each other. They can generate the same magnetic field lines. Okay, although the structure are different. This is a magnetic bar, this is a current carrying coil, but we will say they are equivalent to each other because they can generate some result that are the same. Okay, this result means the B field line they generate. Okay, so and actually here is mentioned that the B field generated by the by this magnetic dipole on this z-axis is actually having this expression B equals mu naught over 2 pi, and then this mu is actually the magnetic dipole moment. This mu and this mu are totally different. Okay, this is the permeability, this is the magnetic dipole moment. Okay, and then the z cube, z is the z-axis. Okay, z-axis coordinate. Okay, here mu is the dipole moment of the coil, and this equation apply only when z is much greater than the dimension of the coil. Okay, so if your memory is good enough, then you should remember. Okay, we have actually learned the E field generated by a electric dipole, or at that time it only call it a dipole, or here full name is electric dipole. Okay, so we have electric dipole generate E field along the z-axis, having this form, and then you can actually compare this expression with this one. Okay, so you can see this is actually E equals 1 over 2 pi epsilon naught and then 2p over c cube. Okay, so these two expression actually takes the same, have the same form. Okay, so it's somehow like starting from this one and then you change it to that one. You only need to change the E field to B field, and then change epsilon naught to 1 over mu naught, and then you change, this is the electric dipole moment, change it to magnetic dipole moment, and that's it. So it is also a form of duality， 就是那个对称性，就是 E field 跟 B field 的对称性，就是你把电场那边的物理量，把它转成相对应的B field 的物理量但是有一点小 trick， 就是之前提过的，就是 epsilon naught 它对应到的不是 mu naught， 是 1 over mu naught mu naught 的导数才会成立。Okay, so actually we will try to derive it rigorously rather than just by using the duality. Okay, so so here it also mentioned that we have two ways in which we can regard a current coil as a magnetic dipole. So the first point is it experiences a torque when we place it in an external magnetic field. Okay, so it means that if we put this current coil between the uniform B field, okay, it will rotate. So this rotation is due to this torque. Okay, And yeah, if you still remember, previously we defined this NIA to be the magnetic dipole moment. The mu equals Ni times A vector. Okay, so this is the magnetic dipole moment. So this one turns to if we write it in a vector form, it can be written as tau equals mu cross B. Okay. And we say that the current coil and the magnetic dipole are equivalent, means if we place magnet bar, yeah, somehow in here, so it will also rotate. It will also rotate. So yeah. And the second point is that it generates its own intrinsic magnetic field or B field. Okay, should be B field given for a distant point along the its axis, just as what I mentioned. So this one and the magnet bar will generate the same form of B field lines. Okay, so we'll call them equivalent to each other. Okay, so this is actually the derivation for the for this expression. Okay, so here is the current coil. Is actually a circle, but it's just a cross section. So we only see somehow like a line, but actually it's a circle. But we just see it from it's actually a circle, but we only see it on this side, so we only see a line. Okay, so along this this circle, okay, so on the left side, okay, is like the current is going out of the page, and this is going into the page. Okay, so it is somehow like we have the current like this. Okay, somehow like counterclockwise. Okay, so actually we want to know the B field along this z-axis. This z-axis is the axis of this circle, which means the line going through the center of this circle and then also perpendicular to this circle. Okay, so this is the z-axis. And for instance, we want to find the B field at this point P, and as usual, we would like to separate this circle into many small segments, and then we find the dB, the B field generated by each segment, and then we try to add them together is using an integration. Okay, so for instance, this ds will generate B field at point P. We can use the Biot-Savart law to find the expression of dB, which is like dB equals mu naught over 4 pi and then I times ds cross r hat. Okay, ds, okay, this current is going out of the page, so ds is also going out of the page, and r is starting from this segment to the point we concern. So this whole line is actually the r, and r hat is the unit vector pointing to this upper right direction. Okay, so this is r hat here. Okay, so actually we have a mu naught over 4 pi I is a known variable, and then ds is this one, r hat is this one, and then over r square is the length of this part. Okay, so here dB, okay, this is the magnitude. Okay, so we should know the direction. Okay, of course we should use the right hand rule. Okay, right hand rule. The cross product is ds cross r hat. Okay, so you use your forefinger pointing out of the page and then cross it to the top right. Okay, so top right. So your thumb will point to the top left direction. Okay, something like this. You can try to play with it by yourself so that you can familiar with the right hand rule. Okay, so so dB is actually in this direction, and we can also observe for this part, for this ds, okay, or maybe ds prime, okay, what is the db prime generated by this part, so that we can determine whether the perpendicular component counts, or whether the parallel component counts, or whether the other components cancels. Okay, so let's see. So this is ds prime, and this is the r hat, maybe r prime hat for the ds prime. Okay, so here we still have ds prime cross r prime hat. Okay, so actually this ds prime is going into the page, and then we cross it to this top left direction. Okay, so this is the r hat direction. Okay, this is actually the r, r. This is r. Okay, so going into the page, crossing to the top left. So this db prime is actually pointing to the top right. Okay, so we can clearly see that db perpendicular cancel each other. So we only consider the db parallel component. Okay, so here we already write db parallel is actually this one is pi over mu naught over 4 pi, and then I is here, and then ds is here, and then this is 1. The magnitude of this unit vector is 1, and then cosine of alpha. Cosine of alpha means that alpha is the angle between ds and r hat. Okay, ds and r hat. So which is actually so which is actually this angle. Which is actually this angle. So cosine of alpha. ds cross r hat. Okay, so yeah, so we have a cosine of alpha here. So actually here we need to find cosine of alpha in terms of s, or in terms of z, so that we can actually do the integration. Okay, so here we try to plug in r equals r squared plus c squared. R squared plus c squared. So what is r? R is this one, and then z is this one, and then r is the radius of the coil. Okay, so according to Pythagorean theorem, we have r equals to square root of capital R squared plus c squared. And then cosine of alpha is actually capital R over small r, and then small r is actually having this expression. Okay, so cosine of alpha is like this, and here db parallel. Okay, so we can just plug in this one to db parallel. So we have a mu naught I over 4 pi going to here, and ds is placing here. Okay, so okay, all these are placing here, and then and then we should substitute the expression of cosine alpha and r into this part. Okay, so that here we have a r, and then this one, and then multiply by the square of this one. So we still have this term to the 3 over 2 power. Okay, just as what we did before. Okay, and then finally we can finish this integral. Actually, all these variables are independent to ds. So finally, all this stuff going outside, and we just integrating ds, which is a circle. So integrating this ds is nothing but 2 pi r. Okay, so actually this one is nothing but 2 pi r. Okay, so this 2 pi and 4 pi partly cancel, only reduced to 2, and then we have r and r, so we have altogether r squared in the numerator, so the expression is simply like this. Okay, so yeah, so we have the expression of b in general for this z-axis, but we still have this z is much larger than our assumption, so which means that we also have this far field condition. So in such a way, the b will be approximately equal to this expression. Okay, because z is much larger than r, then which means that we can just ignore this term. We can just ignore this term. So this c squared to the 3/2 power becomes c cubed. Okay, becomes c cubed. So b equals this one. Okay, actually, this is already done, but we want it. We want the form to be somehow like this, using the magnetic dipole moment as the result. So we should do some simple algebraic computation so that we can transform it to the final form. Okay, so actually, this expression we try to multiply pi on both the numerator and the denominator so that it doesn't change anything. And here, pi r square is actually the area of a circle. So this part is actually a. And and also finally we can consider IA to be the magnetic dipole moment. And of course you may say, oh, the magnetic dipole moment should be NIA, but here we only consider single term. Okay, so if we have multiple term, then we can just getting the similar result just by multiplying n. So yeah, so here you can just pretend that n is 1 here. Okay, if we have multiple term, we automatically have this n, so it becomes the general NIA, which is the magnetic dipole moment. Okay, so finally this term we can write it as a mu naught. We can write it as a mu, so that this expression is is the proof of this equation. Okay, so here we have an additional example to conclude this this chapter. Okay, so here we can see it says two circular arcs, okay, have radii A and B. Okay, this is one circular arc. This is another one, and then subtend angle theta is 74 degree, carrying current I, and share the same center of curvature P. Okay, so so they are concentric and sharing the concentric circular arc. Okay, 就是同心的一个圆弧，就是 P 点。And then what are the magnitude and direction into or out of the page? Okay, of the net magnetic field at P. Okay, 就是问那个 B field 在 P 点的 B field 到底多大 ？OK， 就被这个结构所产生的 B field。Okay, so actually we can simply consider for this part and this part, it will not generate any B field at point P. Yeah, because simply by Biot-Savart law, you can see that this ds for this part, this ds for this part. Okay, and actually the r is actually pointing to that direction. Okay, and then r is pointing to this direction. Okay, so in such a way, or the r head also points to the same direction, but with a unit length. So you can simply see that this ds cross r head will be 0, because these two vectors are either pointing to the same direction or pointing to the opposite direction. So it will feel like sine of 0 degree or sine of 180 degree are both 0. So this segment and this segment won't contribute any B field at this point. So the only two segments that will contribute is this longer circular arc and this shorter circular arc. Okay, so actually B at point P is actually mu naught I theta over 4 pi B. Okay, we just make use of the formula we just derived previously, actually yesterday. Okay, so this part is due to the shorter one. Okay, this term is due to the shorter circular arc. Okay, mu naught I, and then theta is this angle, and then 4 pi B is the distance. And then for this part, okay, we have a subtraction sign, and then minus this mu naught I theta over 4 pi A. Okay, why we have a positive for this term and negative for that term? Because you can clearly see that, okay, the current direction is somehow from right to left for the shorter arc, and then the direction is from left to right for the longer arc. Okay, so actually we can simply use the right-hand rule to determine the direction of the B field generated by each of them. Okay, so the B field generated by this shorter one, okay, you use your 4 fingers follow the direction of the current. Your thumb will be pointing out of the page. Okay, so pointing out of the page. And for this longer one, you use your finger following the direction of the current, and then your thumb is pointing into the page. So yeah, so this B field generated by this part is pointing out of the page, this part is into the page. And yeah, and somehow observing the magnitude here, you can see that this one is stronger, this one is weaker. Yeah, because somehow like this point P is closer to this arc. Okay, so we have this term to be positive, that term to be negative, and finally we will consider, okay, the direction. The direction is actually out of the page. And of course we can also calculate this magnitude of B field. So we can simply do some algebra. So mu 0 I over and theta over 4 pi, and then times 1 over B minus 1 over A. Okay, we just factor the common factor. Group the common factor out, and then we can do the substitution so that we can press less button for the calculator. Okay, so for this one, mu naught is 4 pi times 10 to the negative 7. So this whole thing is 10 to negative 7, and then times I is 0.411, and then times 74 degree. Okay, but actually this theta should be in radian, so we need to change the degree into radian, okay, by multiplying pi and then divided by 180 degree. Okay, and then times 1 over b. 1 over b is 10.7 centimeter, so it's 0.107, and then minus 1 over 0.135. Okay, so this is it, and the value is 1.02 times 10 to negative 7 Tesla. Okay. Okay. Okay, and then we have another one. Okay, so here it says a long circular pipe with outside radius R equals 2.6 centimeter carry a uniformly distributed current I into the page. Okay, so it means this part. Okay, 这个空心的就是一个管子嘛，就是一个管子有一个均匀的电流进入这个平面的into the page. So a wire runs parallel to the pipe at a distance of 3R from the center to center. Okay, so here we have a wire. Okay, the distance is 3R from this wire to the center of this pipe. And then find the magnitude and direction into or out of the page of the current in the wire such that the net B field at the point P, okay, the point P is out to the wire and 2 out to the center of this pipe. Has the same magnitude as the net magnetic field at the center of the pipe, but is in the opposite direction. Okay, so it means that we need to find the B field at point P, and also we need to find the B field at point C. Okay, so we should have a BP and BC. Okay, so these two B fields should have the same magnitude, but the direction is opposite. Okay, so we need to determine how large the current of the wire. Okay, so first we try to find the expression of BC, which means the B field at the center of this pipe. Okay, this is easier because this pipe won't generate B field at its center, at this center. And actually, this wire will generate B field at this point, Yeah, at this point. So BC should be mu 0 IW. Okay, so we consider this is the IW. This is the IW. And then over 2 pi and then 3R. Okay, so you can consider this is a long straight wire, so it will generate B field somehow like this. Okay, many concentric circle as a B field line. Okay, so this is the expression. Okay, so this one is actually mu 0 IW over 6 pi R. Okay, so easier for the BC, and the direction is pointing to the left side. Okay, pointing to the left side means we now assume that this IW is going into the page. Okay, yeah, we just assume this IW is going into the page. So maybe you ask, how do I know it's into the page or out of the page? Actually, it doesn't really matter. Okay, if the answer is actually going into the page, then your answer will be a positive value. Okay, then nothing special. And if actually the current is going out of the page, then the answer will be a negative side. And following that, if you assume the current is going into the page with a negative side, then which means that the current is actually going out of the page. Then yeah, so no matter what you assume, then as long as you calculate correctly, then you will still get the correct answer. Okay, so so the next step is to find BP. Okay, BP. BP will there will be two parts. Okay, one part is still contributed by this wire, so it is actually mu 0 IW over 2 pi times R only. Okay, so from this one to the point P is actually R. Okay, so yeah, something like this, and then minus. Okay, this thing is going into the page, so the B field generated by this part will be actually pointing to the right side. Okay, the the component generated by the wire at point P will be pointing to the left side as this one, okay, but this part will generally be pointing to the right side, okay, so we'll have a negative sign here. So minus mu 0 I over 2 pi, here we have 2R from the center of here up to this point P, okay, this is 2R, this is 2R. So the overall expression will be like mu 0 IW over 2 pi R minus mu 0 I over 4 pi R. Okay, nothing special. And here we should have BC equals negative BP. BC equals negative BP. Okay, so let us let me see. Okay. So let us try to put this here. Okay. So here we should have BC equals negative BP. Okay. So we have mu 0 IW over 6 pi R equals, okay, putting a negative sign here. So we should have mu 0 I over 4 pi R minus mu 0 IW over 2 pi R. Okay, then we can just remove it. Okay, so we have this expression. So we can try to do some simplification, do some cancellation, or the mu naught cancel, or the pi R cancel. Okay, so it remains some IW and the numbers, which can be easily handled. Okay, so this term has IW, this term has IW also. So we just move this term to the left side. So it is actually IW 1/6 plus 1/2. Okay, will be 2 over 3. 2 over 3. IW equals I over 4. Okay, so actually IW will be I times 3 over 2 times 1 over 4. Okay, which is 3 over 8 I. And actually, what is I? I is this 8 mediate. 8 mediate. So it is actually 3 over 8 times 8, which is 3 mediate. 3 mediate, which is a positive value. Okay, so just as what I mentioned, if it is a positive value, so it means it just follows the direction we assume. So IW is going into the page. Going into the page. Okay.